Hi guys, this is a video on standard unique pointer. This is a smart pointer in C++ that solves a particularly tricky problem for us. First, let's understand what the problem is. Remember that every object that you allocate with new, you have to delete with the delete operator. And that sounds simple in theory, however, it's proven to be very difficult in practice. For example, it's easy to forget that the throw keyword terminates a function early. This is a well-intentioned function I wrote up to illustrate the issue. Let's say at the beginning of this function, I allocate an array with new. That looks fine. At the end of the function, I remember to delete the array with delete. That looks fine too. Most of the time, this is fine. Now, let's say there's a possible error condition halfway through the function. So we say if something goes wrong, then we throw an exception, and that's also the right thing to do to handle errors. However, there's a memory leak bug here because we forgot that when we throw, the function terminates immediately, and we never deleted temp array. So there's a memory leak if the error condition happens here and we throw an exception. It's really easy given human nature to make that kind of mistake because when we're writing this code down here with the exception, we're focused on dealing with this error condition, and we probably don't have in mind the context of the beginning of the function and the end of the function that did the new and the delete stuff. That was something else we were thinking about at a different time. So there's plenty of examples of forgetting new and delete and getting it wrong. It's proven to be pretty difficult. So the solution that we have in C++ is combining the RAII idea with smart pointers, or using that idea to create smart pointers. Remember that a RAII conformant class frees all of its resources in its destructor. That means that resource allocation is done in constructors and other initialization functions, and resource freeing or deleting is done in destructors. The constructors and destructors handle it all. It should all be handled automatically and work consistently for us without bugs. Now, one convenient aspect of destructors in the C++ language is that they are automatically called when a variable goes out of scope. When a variable goes out of scope, it's not visible anymore. That object is destroyed. Part of that destruction process is calling the destructor. So what that means is we can create something called a smart pointer. A smart pointer is an RAII style template class, and the pointer class represents a pointer to a dynamic memory object. The destructor of this pointer class automatically frees the dynamic memory object when necessary. And it turns out to be possible to get this right so that all of the deleting is done automatically by this smart pointer class. Programmers using the class like us don't need to think about it. So there's a best practice in C++ using version C++11 and on where smart pointers are available, which is to use a smart pointer instead of a raw star pointer and to use the smart pointer operations instead of new and delete. If you do that and use these things as they're intended, then that will eliminate memory leaks and double delete bugs. So that's a huge win. All we have to do to eliminate these really tricky bugs is use smart pointer classes the way that they're intended to. So we don't have to, if we do that, we don't have to think about new and delete anymore. It's just handled for us. This video explains the unique pointer, which is the simpler of the smart pointer types. Later, we're going to go over the shared pointer, which is a little bit more complicated to handle a case that comes up when we deal with linked lists. So here's my example from earlier that's been refactored to use standard unique pointer. The main difference is that when I allocate temp array, I'm not using a raw pointer with the star symbol. Instead, I'm using a std unique pointer to t. That is a template class that is a unique pointer to an object of type t. Here I'm allocating with new. There's actually a way to get around that I'll show you in a moment. But temp array is now a unique pointer, a smart pointer. It's not a raw pointer. So I don't need to worry about deleting it. There's this comment here, there's no explicit delete anywhere. In particular, the end of the function doesn't need to do delete because when the function reaches its end, temp array goes out of scope. This temp array variable does not exist anymore when the close brace happens. So temp array gets destroyed, temp array's destructor is called, and that destructor is responsible for doing the delete on this array. We don't have to think about it. That's great. Also, the exception bug is now solved because if this condition is true and we go into this if body and throw an exception, the function ends at this moment that means temp array goes out of scope, and the compiler is smart enough to know that means temp array is destroyed, call the destructor, and free the object. So we don't have to think about it. So it's rather subtle that implicitly these bugs just go away when you use unique pointer, but that's kind of the idea, is to solve a problem for us. So a little more about what unique pointer is. It's using the word unique because a unique pointer is the only pointer to an object. This actually covers most use cases of new and delete. Most often, when you're allocating an object with new and delete, it's a member function or a data member of a class. A private data member is something that no other object owns. The class that has that pointer is the only one that should do new and delete on it. That's part of the RAII idea. So most use cases, I might estimate 80% of all use cases of pointers can be handled with unique pointer. And as I mentioned later, we'll see there is something called a shared pointer that handles the other use cases when you need multiple pointers into the same object. Standard unique pointer with template parameter t is a pointer that owns an object of type t. The destructor automatically deletes the object when the pointer is destroyed. Also, I'll note that a unique pointer can own nothing, just like a raw pointer can be null, a unique pointer can be null. So here are the major operations we need to know about on unique pointers. There's more of them. I encourage you to read the standard documentation to see all of the things that unique pointers can do, but these are the ones that we need to go forward right now. The default constructor on unique pointer creates a unique pointer that owns nothing. In other words, it points at null. There's a single argument constructor that takes a t star object. So you can construct a unique pointer of parameter t by giving it a t star object. The spirit of this is that that t star object was created with new. So you would allocate with new inside the parentheses here. That makes the pointer own that object and take responsibility for freeing that object with delete later. Operators on unique pointer work just like they work on raw pointers. For example, if you use the star dereference operator, that yields a reference to the owned object, just like would happen with a raw pointer. Likewise, the arrow operator works on a unique pointer, just like it would work on a raw pointer. There's also a get function. We're trying to minimize the use of raw pointers. However, sometimes you really need it. One example is if you're using legacy C code or C++ code that demands to have a pointer, you might need to get the T star style pointer, so get is available for that. Also, if you want to use the array subscript operator, you need to subscript off of a raw pointer, so the get function lets you do that. I have an example of that use case in this video. Finally, there's a member function pointer.swap. You have to give it another unique pointer of the same base type that exchanges the contents of the two pointers, and that's useful in some cases. In particular, in the vector data structure that we're going over very soon, that is a useful operation. Finally, there's a helper function to eliminate your need to use the new operator. It's called makeUnique. This is a top-level function. It's not a member function. So you just call makeUnique and pass in some arguments, and that's equivalent to passing those arguments to the constructor of type t. So doing a new t with those arguments and then putting that newly constructed t object in a unique pointer. So makeUnique returns a unique pointer to t for you. It calls the constructor. It's a convenience. It looks a little nicer, and it means you never have to see new if you do that. Here's an example of how we could refactor the array class from earlier in our course to use a unique pointer. So just like before, our array class has an int size, and it has a private data member of a pointer to an elements array. However, now that's a unique pointer. It used to be a t star raw pointer. Now elements is a unique pointer to t. Up here I have the default constructor that creates an empty array, and size is initialized as usual. Elements is initialized with a new t. That's also like before. We could actually use makeUnique here as well. The big win for us is that we don't need to write the destructor ourselves. Remember that the default destructor of a class simply calls the default destructors of all of the data members. So when an array is destroyed, the destructor of unique pointer is called, and that is what is responsible for deleting elements. So I do not need to write any code to delete elements. That is handled for us implicitly, which is great. There's a labor savings in two places. For one thing, I don't have to write that destructor To be fair, that destructor was only one line long. It's not really a killer. However, the rule of three said if you write that destructor, you have to write these two other technical long functions. However, now I'm not writing a destructor, so the rule of three does not come into play, and I don't have to write the copy constructor or copy assignment operator. It turns out that actually the implicitly defined copy constructor and implicitly defined copy assignment operator work fine with unique pointer, and that's part of the purpose of unique pointer. So all of that stuff is just gone. We don't have to deal with it anymore, which shows the benefit of using unique pointers in these kind of classes.